It'll help you with drawing all the structures if you just memorize how many bonds these different elements tend to form. We already said carbon was tetravalent. Hydrogen forms 1 bond. Oxygen normally forms 2. Nitrogen normally 3. And halogens normally 1. Just to show you how, and there is a pattern. Let's not do X. There is a pattern on the periodic table if you want to look that up. But let's just look at oxygen. Oxygen has 6 valence electrons. So in order to have 8, it needs to have something come in on 2 sides, providing an electron so that it can have 8. So it ends up with 2 bonds. So basically, on any of these elements, if you look at how many unpaired electrons they have, so nitrogen has 5 valence electrons. That's why it forms 3 bonds, because it needs 1 there, there, and there. Let's look at ways to draw organic structures, because we're going to need to learn some shortcuts. Most people don't draw the entire structure every time. So this is a simple molecule, 3 carbons in a row, and it has its hydrogens attached to it. On this structure, I'm showing every bond and every atom. Hydrogen atoms are the first thing to go because there are a lot of them, and we just understand that they're there. I showed you this one because this is how the lab manual shows these, with these kind of long bonds, but it's understood that there are really hydrogens out there, so these are the same. I'm going to take that a step further in my notes and just show the carbon backbone. And you need to understand that there are really hydrogens attached to that. In fact, in a minute we will look at how you can figure out where all the hydrogens are. So that this in black is the same compound as the others. Also, we might bend them. In other words, like this, you need to know that these are the same thing. It doesn't matter that it's bent. The molecules aren't straight anyway. We've flattened them to put them on a piece of paper or on the screen. They're actually kind of zigzaggy, but you know what? The single bonds rotate, so their shape is constantly changing as they move around. Another shortcut we'll take is the condensed formula. This is condensed. A condensed formula shows the carbon backbone, and for each carbon it shows what's attached to each one. So the end carbon had, bring this down, this end carbon had 3 hydrogens attached to it, so that's why I show H3. Then a single bond to the next carbon, and we need to understand that that bond, this bond, is between carbon and carbon, not carbon and hydrogen. Carbon is the backbone. The middle carbon had 2 hydrogens, so that's where I get the CH2, and so on. The one on the end has 3. Sometimes we shorten that a little bit more and not show the bonds. If there's a double bond, we will show that. A double bond would look like an equal sign. But if there's no bonds shown, you can assume that they're single. Writing the condensed formula makes it simple if you're entering on a computer. You don't have to get out the draw tools and stuff to do that. So all of these structures that I've drawn here are the same compound. Whoop, there we go. Okay, let's look at how we can figure out how many hydrogen atoms they would have. Let's look at this one. All you do is you use the rule that you know about carbon, that carbon normally forms 4 bonds. And so when I look at each carbon, this one has 1 bond that is shown, so it must have 3 bonds to something that's not shown. Like I said, hydrogen is the element that we leave off the most. If we have an oxygen or a nitrogen, we show those. We always show those. but hydrogen is left off. So next carbon has 2 bonds that are shown, so it must have 2 hydrogens. The next carbon has 2 bonds that are shown, so it must have 2 hydrogens. And then this one on the end, it has 1 bond that is shown, so it must have 3 hydrogens. So this is C4H10. There's a little formula for alkanes, so that means single bonds only with no rings. And I'll show you what that means in a minute, but basically it is the number of hydrogens equals 2 times the number of carbons plus 2. The no rings part is this. You can have a compound that has a ring instead of having a chain. So this formula only works for this case if there's no rings and only single bonds between carbons. Let's see how many hydrogen atoms this one has. I'm just going to draw dashes, and then the question is, what do you do with a double bond? A double bond counts as 2 bonds. So there are 2 bonds there and 1 there. That only leaves 1 for the hydrogen. This carbon on the end already has 2 bonds, so it has 2 hydrogens as well. Let me go ahead and add my H's on here. So this is C4H8. Don't let it bug you that I drew these out at an angle, these hydrogens on the end. It doesn't really, it would if I drew one up and one down, it would mean the same thing. I'm just representing what I know is the true shape of that molecule. Sometimes we do that if we know the shape, and at that carbon, those kind of go out at an angle like that. Okay, so we notice this formula does not follow that equation up here. And why doesn't it? Well, because this has a double bond, and so that equation does not apply to it.